Welcome, curious minds, to another deep dive. Today, we're really plunging headfirst into something foundational. It often seems complex, but it's fascinating. The language of chemistry.
Yeah.
Yeah, so our source today is an educational PDF really designed to introduce these fundamental ideas. And our mission, well, it's to unpack how chemists actually talk to each other, what chemical reactions truly are, and maybe the coolest part, how you can spot these transformations happening literally everywhere. Get ready for some, aha moments as we decode how elements and compounds interact and change.
Absolutely. And we want to go beyond just the symbols and the equations. This deep dive is really about the why behind them, how they create this kind of universal language for the molecular world. It just makes chemistry clearer, more accessible, I think.
Okay, let's unpack this then. Chemistry, it involves a huge number of elements and compounds, right? Trying to write out their full names, like every single time. It would just be, well, completely impractical.
Exactly. Completely. That's precisely why chemists develop these shorthand notations. We use symbols for element C for carbon, O for oxygen, and formulae for compounds, H2O for water, NaCl for salt.
Simple examples, but powerful.
Very. And it's not just convenient, it makes it universal. Scientists everywhere use the same system. And this shorthand naturally extends to describing chemical reactions. We use equations for those.
So it's like a universal code. Makes complex stuff concise, understandable, like a grammar for how matter changes. Okay, here's where it gets really interesting for me. Maybe the biggest aha moment. Defining a chemical reaction. You mentioned transformations. Can you break down what's really happening? What makes it different from just, say, mixing sand and salt?
Right. A chemical reaction isn't just mixing. It's a fundamental chemical change in matter. It involves transforming into one or more completely new substances, not just a physical change like ice melting.
So new stuff has to be made.
Precisely. And crucially, there's always a transfer of energy involved, either released or absorbed. The stuff you start with, we call those reactants, and the new substances formed. Those are the products.
Reactants, products, okay.
And both reactants and products, they're pure substances, elements, or compounds. That consistency is key.
So the atoms themselves, they're not destroyed or created from nothing. Are they just shuffling around like Lego bricks being rebuilt?
That's a great analogy, exactly. During a chemical reaction, the atoms from the reactants just rearrange themselves.
Right.
They break old bonds, form new ones, and create these new products. But, and this is vital, the atoms are neither destroyed nor new atoms are formed.
Wow.
They're all still there, just in a new configuration. This actually lays the groundwork for a really big idea we'll get to later.
That's kind of mind-blowing when you think about it. Like a candle burning, we all see that. Candle wax, it burns in the air, and poof, you get carbon dioxide, water vapor, and you definitely feel the heat, see the light. That's energy being released. It's a total change.
It is. And the simplest way to write that down, especially when starting out, is a word equation. Just use the names. So for the candle, maybe, candle wax plus oxygen arrow, carbon dioxide plus water plus energy, something like that.
Okay, just the words.
Or another example, sodium oxide plus water arrow, sodium hydroxide, straightforward. It just shows the before and after.
So if atoms are doing this invisible dance, how do we spot it? How do we play chemical detective? Our source mentions some clear, observable characteristics, right? Telltale signs.
Yes, exactly. The first one, often quite obvious, is the evolution of a gas.
Right. Activity 1 in the source talks about mixing sodium carbonate, that's a white solid, with dilute hydrochloric acid, and bam, you get this brisk effervescence, bubbles everywhere. Fizzing, that's the carbon dioxide gas forming, right? And the source says the test tube gets warm too, so heat is given out.
Absolutely. That fizzing, that effervescence is a classic sign. We see it again in activity 4, mixing baking soda, sodium bicarbonate with vinegar, acetic acid. You get really strong bubbling there too. Again, carbon dioxide.
But you have to be careful, right? Like, boiling water makes bubbles, but that's just water turning into steam, not a new gas.
Excellent point. It has to be a new substance forming as a gas. Another really noticeable sign is a change of color.
Oh yeah, this one's cool. The example of adding iron pieces to that bright blue copper sulfate solution. Slowly, the blue fades, it turns light green, and you get this reddish-brown stuff forming. That's copper.
A very clear visual transformation. Or activity 2, heating sugar. First it melts, then it turns brown, then this black residue, charcoal, it's totally lost its sweetness.
And you see water vapor coming off, the sugar is chemically changed, gone.
Exactly. And activity 3, Heating green copper carbonate, it turns into a black solid copper oxide, and again, CO2 gas comes off.
Then there's the formation of a precipitate. That sounds technical.
It just means an insoluble solid forming when you mix two solutions.
So like two clear liquids mix and suddenly cloudy stuff or solids falling out.
That's it. The example given is adding barium chloride solution to sodium sulfate solution. Instantly, you get this white precipitate of barium sulfate. Two clear liquids make a white solid.
Wow. And activity 5 mentions mixing potassium iodide solution and lead acetate solution. That makes a bright yellow precipitate of lead iodide. So you get the solid and a color change, 2 signs at once.
Sometimes you do get multiple signs. Another key one is a change of state. Meaning a reactant, say a solid or liquid, turns into a gas product. Or maybe two gases react to form a liquid or solid.
Ah, okay. Like hydrogen gas burning and oxygen gas. 2 gases react.
And they form water, which is normally a liquid. Gas to liquid.
Or that other example, ammonia solution near hydrochloric acid. 2 gases, basically.
React in the air to form dense white fumes, which are actually tiny solid particles of ammonium chloride, gas to solid.
Fascinating. What about smell? Can that be a sign?
Definitely.
Yeah.
A change of smell could be a very strong indicator. Some reactions produce really distinctive odors.
Like heating ammonium chloride with sodium hydroxide. That gives off ammonia gas.
Which has that really strong, pungent smell. Unmistakable.
Or the infamous one. Heating iron sulfide with acid produces hydrogen sulfide.
Ah, yes, the classic rotten egg smell. You don't forget that one.
Never. Okay, one more big one. Energy.
Right. Almost every chemical reaction involves a change of energy. It's either released or absorbed.
Reactions that release energy, often as heat or light, are called exothermic.
Correct. Exo meaning out. Think of adding water to quicklime. It gets incredibly hot. Or emitting magnesium, that dazzling white light. Burning coal gives heat and light.
And activity 7, mixing sodium hydroxide and hydrochloric acid. The beaker just gets warm, a subtle heat release.
Exactly. On the other hand, you have endothermic reactions. Endo meaning in. These absorb energy.
Like photosynthesis. Plants need sunlight energy to make food.
Perfect example. Or heating calcium carbonate. It needs to absorb heat energy from the surroundings to break down to decompose.
So these reactions actually make their surroundings colder, potentially.
They can, yes. They draw heat in.
Okay, so we know the signs, but what actually makes a reaction happen? Are there specific conditions needed? It's not always automatic, is it?
No, not always. It's like baking. You need the right ingredients and the right conditions. First, usually close contact. Reactants need to be mixed to actually touch each other at the molecular level.
Like sodium reacting with water, it happens instantly on contact.
Violently, yes. And that's why we store sodium under kerosene to keep it away from air moisture. No contact, no reaction.
Makes sense. And sometimes just mixing solids isn't enough. You need a solution.
Often, yes. Activity 8 shows this well. Mix solid salt and solid lead nitrate. Nothing happens. Dry.
Right.
But dissolve each one in water first, make aqueous solutions, and then mix them.
Then you get that precipitate, the solid lead chloride forming instantly.
Exactly. The ions need to be free to move around in the water to find each other and react.
Ah, like Eno's powder.
Yeah.
Or any fizzy antacid. It just sits there in the packet.
Dry, inert.
Until you pour in water, then fizz, bang, bubbles. The water lets the reaction happen.
Precisely. The solution allows the interaction.
What else? Heat seems obvious for some.
Yes. Many reactions need heating to get started or to keep going. Like iron and sulfur forming iron sulfide, you need to heat them.
And light, photosynthesis again.
Photosynthesis is the prime example. But other reactions are light sensitive too, like how old photographs develop.
And electricity.
Some reactions are driven by electricity. Passing current through water breaks it down into hydrogen and oxygen gas. That's electrolysis.
Okay, one more condition mentioned. A catalyst. What's that about?
Ah, catalysts are fascinating. They're substances that can change the rate of a reaction, speed it up, or sometimes slow it down. But here's the key. The catalyst itself doesn't undergo any permanent chemical change. It helps the reaction happen, but isn't used up.
So it makes things happen faster, maybe at lower temperatures, without being part of the final product.
Exactly. Like manganese dioxide speeding up the breakdown of potassium chlorate. Makes it much easier.
Okay, so we've got the shorthand symbols, the signs of reactions, the conditions needed. How do we formally write these reactions down using the chemical language?
Right, using chemical equations. We talked about word equations like carbon plus oxygen, carbon dioxide.
Yeah.
The more powerful way is the symbolic or chemical equation, C plus O2, CO2. It uses the symbols and formulae. It's the ultimate shorthand description. Saves space, time, energy. conveys so much.
And the structure is pretty standard, right? Reactants on the left,
Products on the right,
correct,
separated by an arrow showing the direction of change.
arrow pointing from reactants to products. And if there's more than one reactant or product,
You use a plus sign plus between them. So like A plus B, C plus D, that's the general form.
and you mentioned using molecular formulas like H2O2Cl2.
Yes, because elements like hydrogen, oxygen, chlorine usually exist as pairs of atoms bonded together as molecules, H2O2Cl2. Individual atoms like H or Cl are generally too reactive to exist alone for long.
Got it. Now, there's this idea of balanced versus skeletal equations. What's the difference?
A skeletal equation just shows the reactants and products using their correct formulas, like H2 plus Cl2 HCl.
Okay, hydrogen plus chlorine makes hydrogen chloride.
Right. But look closely. You start with two H atoms in H2 and two Cl atoms in Cl2. But the product HCl only shows one H and one Cl.
Ah, the atoms don't match up on both sides. That's unbalanced or skeletal.
Exactly. A balanced equation adjusts the numbers in front of the formulas, coefficients. So the atom count is equal on both sides, for example. ZNO plus C, ZN plus CO. One zinc, one oxygen, one carbon on the left. One zinc, one carbon, one oxygen on the right. That's balanced.
Why is balancing so important? Does it really matter if the atoms don't visually add up in the equation?
Oh, it matters fundamentally. It connects back to that crucial principle, the law of conservation of matter or law of conservation of mass.
The one you mentioned earlier, atoms aren't created or destroyed.
Precisely. Matter cannot be created or destroyed in a chemical reaction, only transformed. So the total mass you start with must equal the total mass you end with. And since mass comes from atoms, the total number of each type of atom must be the same on both sides of the equation.
Ah, so balancing the equation is basically making it obey that fundamental law.
Exactly. That's why chemical equations must be balanced to accurately represent reality. It ensures we account for every single atom.
That makes so much sense. It connects the symbolic representation directly to a physical law. But you said word equations don't need balancing.
Correct. Word equations are just descriptive names. Balancing is for the symbolic equations.
And the actual how-to of balancing complex equations.
Yeah.
That's something for later study.
Yes, the detailed techniques are usually covered in higher classes. For now, understanding why it's necessary is the key takeaway.
Okay, so wrapping this up, what's the big picture here? We've gone from symbols to reactions to the laws governing them.
I think the big picture is seeing chemistry not as just symbols on a page, but as the story of how matter changes. Its precise language lets us tell that story accurately, following the fundamental rule that matter is conserved. What goes in must come out, just rearranged.
It really is an elegant system.
It underpins so much of the world around us.
So for a final thought, something for you listeners to mull over, think about something really simple. Toasting bread. You see it change color, right? It gets brown. You definitely smell something new, that toasty smell. Maybe it even tastes different, crunchier. Based on everything we've talked about, the characteristics of chemical reactions, what signs can you spot just in making toast? And what does that tell you, really, about what's happening to the bread on a chemical level? It's not just bread anymore, is it? Something to think about next time you're making breakfast.
Thank you so much for joining us on this deep dive into the language of chemistry. Until next time.